I'm Bodie Long.
I'm Alex Petrov.
I'm Andy Waldo.
And this is Repeat It to Beat It. What did DP1 teach us? It gave Team 20 a lot of confidence in its final solution. It showed a lot of congruency in our team and our process as a whole. There wasn't a lot of friction between us, and there wasn't a lot of push to make any big changes at all, which really made our project consistent. Because though we've made minute tweaks here and there, overall, our final solution is very, very consistent with our first final solution that we had in DP1.
We're going to talk a little bit more about project management. So this is a design structure matrix for all of the tasks that have been completed so far. We're currently at prototyping, and the only task remaining is presentation of final results. And this helped us tremendously in the beginning with allocation of our time resources. We were able to estimate which task would take us a little more time to complete, which task would be sequential, which task would be coupled or parallel. Like for example, tasks B, C, and D don't really depend on each other, so we were able to finish those in parallel. But task E, F, and G, we had to spend a little more time on those because those are very interdependent, so we had to account for that in our time estimation. And this is our Gantt chart for the whole project. We're at April 19th, right there in the right bottom corner, with just a presentation of final results remaining in the last week, with the project ending on May 2nd as specified. And as you can see, all of the tasks were successfully completed up to the point where we are right now. And that takes us to intellectual property and ending.
So before we wanted to show generating and selecting a design, we wanted to take a look at intellectual property and patents that are already existing. So in our actual report, we have a patent search summary table, which allowed us to take a comprehensive look at the certain features of patents and certain limitations that would place on our design, or certain ideas that we could take from it and apply to our design. So one of those patents that we evaluated is called Toy Building Brick, or as we all know it to be, Lego. Now Lego has really been a model of consistency in terms of connecting one brick that they might have made 20 years ago and being able to have it perfectly connect to a brick made today. Now we can't perfectly emulate that, but we want to use that idea of consistency and apply it to ours, because earlier in this process we identified one of our customer needs as having our parts easily assembled, or having a replacement part and being able to insert it into the design with ease. So we want to really be able to mimic that consistency with our own unique way of connecting our parts. And that takes us to concept generation and selection.
So, as we thought up all of our designs, we had to make sure that there was 3 things that they all consistently had. They all had a sensor that would communicate with the Arduino board. They'd have a mechanical component which would be told by the Arduino board what to do, and we'd have a direct application of physics. And with our sensors, we had force sensor, light sensor, and weight sensor. It's pretty easy to tell that the force and the weight sensor would be ineffective because a ping pong ball is so light that it'd be hard to get it to activate those sensors. So we chose the light sensor. Our mechanical components were a DC motor, a DC fan, and a latch release. And we figured out that a DC fan would require calculations that high school physics students necessarily wouldn't be able to complete. And a latch release would be harder to put together, and it would give more % error for the user to endure. So we chose a DC motor because all you got to do is plug that in and it comes pre-made. Our physics applications were conservation of energy, action-reaction forces, and kinematics. We went with conservation of energy because a ping pong ball is so light that friction is relatively negligible, and due to that, the energy is conserved, and it basically simplifies action-reaction forces and kinematics as a whole, so it makes it more effective, easier to figure out, and even more complicated results. So our final solution, called the elevator, we made a mock-up. The ball enters from the right into a cup and then is raised by a DC motor into one of three pathways. These three pathways give the ball a certain speed to reflect off this angled surface, which then cause the ball to fall into three different holes. Two of those holes will lead the ball back to the beginning and it will start all over, but one will let the ball complete the entire BRG station.
And for this final design, we conducted a failure modes and effects analysis, as you can see summarized in this table. We looked at 4 functions, primarily: the cup and motor system, the rebound portion, the return loops, and the exit ramp. What we found out, we estimated the severity, the probability of occurrence and detection of those failures. What we found out is that the most important function, the one most likely to occur, is exit ramp. So we had to work on that. And that's likely due to high severity of exit ramp, just because ball wouldn't be able to circulate through the section, through the station again, if the failure did occur. And also high occurrence of that before we fixed the function, largely due to very complicated nature of angles and heights we had to calculate. So what we did, we adjusted the angles, the incline angles, and we also adjusted the height a little bit to make it easier for the ball to circulate through the station. And that solved the problem, especially decreased significantly the occurrence of the issue, and also severity a little bit, just because the ball wouldn't stop necessarily if the error did occur, but would go through just at a little slower speed. And also we would like to talk about our economic analysis. That's our proposal submitted to VTEPS. We made a couple of assumptions. We assumed our annual profit to be $2,000, the one we calculated in DP1. We assumed our initial investment requirement of $10,000 just to begin our production in the first quarter. We also looked at annual interest rate of about 8% and aimed for a return of investment of 12% for VTEPS. And we proposed 2 models, 2 economic models, one with single payment at the end and the other one with continuous payments at the end of every quarter. And this is our single payment model. As you can see, we get $10,000 in the beginning and we pay back $15,000 at the end. That leaves us with $3,000 net present benefit for our team. And that's how it looks from the perspective of VTEPS. They spent $10,000 in the beginning and received $15,000 back, and that puts us at nice 12% annual return of investment that we were aiming for. However, this other model, the continuous payments model, is slightly worse for us, slightly better for VTEPS. We end up with only $2,000, where VTEPS brings up their return of investment per quarter up to 7%. So we looked at this, we made our estimates, and we decided the single payment model is easier to implement, very easy in logistics, and if both parties find it acceptable, we would like to move on with that model forward.
And to conclude, we wanted to reiterate that throughout this process we've been able to slightly refine and improve our design. We've been able to evaluate been able to evaluate the economics of it, also the concept generation and selection, and that has yielded positive results and a great final product for Repeat It to Beat It. Thank you.
Thank you.